All right, so on the agenda, you can see that we have a quick update on the quiz that you took on forces. The scores were quite good. The mean score for this class was a 94.2, and the median score was 97.2, so very high. Usually when the mean and the median aren't real similar, that means that most people got in a certain range and there were one or two kind of outliers statistically speaking. And so I haven't had a chance to do an analysis of all of them because I still have 6 or 7 students to make up the quiz. I've got a few of them scheduled now to be making them up in the next couple of class days. And so if you are one that needs to make up that quiz and haven't arranged that with me, make sure you talk to me about that so that we can get that squared away, whether you're watching this on video or you're in person. I think everybody took it except for Hannah was out, and you've already worked with me on getting it set up. So I think everybody in this class is good. But if you're watching the video and haven't yet, make sure you communicate with me and let me know. We are starting Unit 7, and Unit 7 kind of has 2 parts to it. So one part is uniform circular motion, which is what we'll be learning today and Friday, and then also next week. And the second half of it is rotational motion, and that's what we'll be covering the first 2 weeks after we get back from the winter break, or ski week, as a lot of people call it. So the 2 halves of this unit, a lot of students find this first half to be about the same difficulty level of what we've been covering. It's a little bit of a shift because we're thinking about things moving in circles instead of straight lines. But if you've had Algebra 2 and you've learned about sine graphs and cosine graphs and period and frequency, some of the things we'll talk about today, there's enough connection to other classes. These 2 weeks leading up to ski week, or winter break, probably not really much more difficult than what we've had. Now the rotation, there's going to be a lot of new thoughts, a lot of new concepts, and that often is a subject area that students find is the most difficult topic of the year. So this Unit 7 does contain some of the more complicated type of problems and some of the more complicated concepts. So make sure you are taking good notes, asking questions. Don't let yourself fall behind. You want to be really careful about that. What we have in store today to introduce this concept of uniform circular motion, and it's such a common concept that you'll often see it abbreviated UCM. Going to do a few quick demos, and then the 2 worksheets I just put on there to remind you guys that are present that you could grab print copies of that. Based on what's happened in my other classes, I doubt if we'll have time to do any breakout groups with that intro worksheet, but that will be the assignment that's today. And for those of you that are on Zoom, at the end of the period when I do assign it, I'll show you where you can find it. And it is on Axis. And then the next assignment I just posted here, again, just to remind me to tell you, you can grab both. We won't be working on that one until Friday. All right, so I have a few demos that I want to show you, but I'm going to stop sharing the screen here. I think that may have been part of the problem last time, was that I had that open. And so it was more difficult to see. And then I'm going to pin this video. So hopefully that maximizes it and allows you to see it a little bit better on the video. So one of the things that we would normally do for uniform circular motion is a lab that I'm going to kind of demonstrate and talk through with you today. And it's a very simple lab. If any of you want to try it on your own, all you need is a piece of string and something reasonably heavy to tie to the string. If you've had chemistry, you might recognize there's just like a rubber stopper here. You could use anything though, just tie it on one end of the string. And then there's a little plastic tube here. You could just take a pen apart, like a Bic pen, take the 2 ends off and you have a hollow plastic tube. Or you can actually do it without a tube. You don't need that. It just makes it a little easier and nicer to handle. But the basic lab would be for you to spin the stopper over your head in as much of a horizontal plane as you can. All right. And the goal, if we were going to tow a gamma of this, so I'll try to take it out of spin without hitting anything or myself. The goal of this would be to tow a gamma to obtain a graphical and mathematical relationship between. And the first item or first aspect that we would try to study is acceleration. And then I would say, okay, well, there's a few things that might affect the acceleration of this. And so a couple things that might affect it. As I'm spinning it, so I'll spin it here, try to get it at a pretty constant thing. I don't want to hit the TV or Hannah or anything, but try to spin it at a pretty constant rate. And then I'm applying a force with my left hand. I just tied a little loop in the string so I can put my finger through it. And I'm just applying a force so that if I take my finger out of that loop, the stopper is going to go flying, right? I need to apply a force. So I'm applying a force just to hold it steady. But if I apply a greater force, you can see that that causes the stopper to speed up and the radius of the circle that it's traveling in to decrease, right? If you had bad internet connection, because I know it kind of comes and goes, if you happen to be foggy or hazy at that point, I'll show one more time. I just try to keep it at a pretty steady pace. And then as I pull with more force, it decreases the radius and increases the rate that it's moving in a circle. So one thing that we would have you check is if you change the force that you're pulling with below, how does that affect the acceleration? That would be one TOA gamma connection. A second one would be, is the radius itself. The distance from the tip of this tube to the center of the stopper. What is that radius? And do you have a small one that you're going at a constant speed? Do you have a larger one that you're going at a constant speed? And how does that radius affect the acceleration of the stopper? So that would be another connection that we would try to evaluate. How does the radius and how does the force connect? All right. And then the last thing we would evaluate is just the speed itself. So if I'm going, let's say I keep the radius constant and I keep the force constant. So I try to keep everything constant that way. So force, I'm not pulling any harder or less hard. I keep the radius constant, but then maybe I just speed up and spin it faster. How does that affect acceleration? Or maybe I just spin it slower. How does that affect the acceleration? All right. And so you'd be finding velocity versus acceleration. What's the connection? Force pulling down below with acceleration. How does that connect? And then the radius. How does that connect? So that's what we would be doing if we were going to do this lab in person. You're going to actually do a simulation. That'll be one of the other assignments on Friday. The worksheet here, that worksheet 1, we're going to actually do in class Friday. And then the assignment will be a simulation of this. And the reason I'm going with the simulation is right now, at least, more than half of my students still aren't on campus. And so with so many of the students not being on campus, I think it's better just to keep it more balanced and have everybody do the simulation. However, for those of you that come to campus, you're more than welcome to try this. Okay, so I've got a box full of these things, and you're welcome to try it and see what it feels like and experiment with what does it feel like to pull with more force? What does it feel like when you have a longer or shorter radius? So, and if you're at home and you want to feel that too, like I said, it's a really simple design. You just need something heavy tied to an end of a string, and then nice if you have a little tube to run it through. And that's all it is. So it's not something you couldn't do at home, but I do have some already pre-made here. So that's what we would TOA gamma, and then I would say, okay, go. You know, you need to evaluate. I'm not going to give you a procedure. I'm not going to tell you what to measure or how to measure it. I'm just, you go. And that's how we normally do things when we're in a normal mode of teaching and learning in this class. But we're not in normal mode. So what we're going to do is try to do the next best thing we can. So if that were your task, just whether you're in the class or in the Zoom, you can unmute if you're in the Zoom. What are the things that I could measure to accomplish that TOA gamma goal? And how would I measure it? What would I measure and how would I measure it?
Remaining distance of the loop by a meter stick or instrument.
Okay, I could measure this distance or this distance, either one or both, just using a meter stick. So that would be one point of data I would want to keep track of.
Which relationship are we finding?
We want to talk about all three eventually. So the force I'm pulling with down here, the radius between the center of the circle and the object, and then also the speed that it's moving at.
Yes.
So we've talked about the radius using a meter stick.
The pulley to measure the force applying on it.
How would I measure that? Any ideas? Again, if you're in the Zoom, just unmute, chime in.
Can you use that force gauge thing?
The digital one?
Yeah.
Yeah. Yeah, we could use the digital. I don't have one out here anymore, but we could use the digital force gauge, connect it to this loop, plug it into the computer or plug it into a TI Inspire and have it measure the force. That's one way. Let's stick with force for a second. Any other ideas on how we could measure the force? Let's say that we didn't have the digital version.
A pulley.
The spring one?
Yeah.
Yeah. Almost every lab that has any physics class is going to have the spring scales. We've already talked about them and used them at least virtually a couple times. So I could, instead of holding it with my finger, hold it with the spring scale. And then as I spin it, I could decide, what radius I want to spin it at and keep that constant. And I could see what the force is at this speed. And what's the force at that speed. And what's the force at that speed. And I could literally measure the force on the spring scale, just like I would on the digital. That's another option. There's a third option. You have an idea?
Oh, put a weight and then find the multiply it by 10.
Good. So demonstrate that as well. I'm just going to demonstrate a couple other things. So I could just put a metal weight on the bottom. So again, just taking one of those metal weights that we've used for a couple of experiments now. This is a 500-gram one. I wouldn't want to be swinging this because it's metal. This is just a rubber stopper, so it's a little bit safer. But I could just hang a weight below. And if I keep it steady, then that weight shouldn't rise or fall. And I know what the weight is. It's 500 grams. That's 0.5 newtons, right? So I could see, okay, what if I speed it up? What happens to the weight? See the weight rising. What if I slow down? See the weight falling, right? Keep it up so don't hit yourself on the head. And then you could adjust the radius, you could adjust the speed, and adjust the weight that way. And then you know the force that's pulling. Now, this is swinging in a circle, and if the string broke, what would the stopper do?
Fly over.
It'd go flying, right? So we know that it has momentum, it has motion. So the only way to keep it flying in a straight line, like Newton's first law says it should, is if there's some force not letting it fly away in a straight line. And so originally the force was my finger pulling it. Now the force is the weight of this block. So I know exactly how much force is required to keep this going in a circle at a given radius and at a given speed. Okay, so we figured out how we could measure the force. We figured out how we could measure the radius. How about the speed that that stopper is moving at? How could I measure that?
You could time how long it takes to go one full circle maybe, and then using the radius, you can find what the circumference is, and that's how far it went.
Excellent, excellent. You actually, that's part of the notes today. I should just let her teach this one. So, yeah, if we know the radius, we can find circumference, right? If you know the radius of a circle, you can find the circumference. And we could time how long it takes to go around. So 1, 2, I could just count it. I was seeing when did it go in front of the owl. It's got a reference point. I'd start it, stop it. Now, so those are some things that FRQ might ask. You want to do this experiment, you need to compare these types of measurements, and so you can find the relationship. What equipment would you use? What measurements would you make? Okay, so we've had that conversation. Another thing they might ask is, okay, they don't tell you that. They say, here's what students did. What could they have done better to minimize their error? Right? So what kind of errors can you see would exist in this experiment based on what I've demonstrated so far?
It would probably be really hard to get the exact time of one full rotation.
Yeah, if I'm looking at this I'm gonna try to start it right when it goes in front of the owl, and I'm gonna try to stop it right when, but so if I'm off at the beginning and I'm off at the end, I have like double fold the amount of error, right? Now, it could be that I was too soon one way and too late the other way, so it cancels out, but I'll never know that. And so that is for sure. My human reaction time is going to be a source of error. Now, a couple things about that though. It's great as a source of error to say human reaction time would potentially make the time measurements inaccurate or inconsistent. You should never say it more generically as just human error, okay? Just saying human error is way too vague. They would not give you any credit for something like that. You would have to say human reaction time is limited, and so that would make our time measurements inconsistent. So how could we improve that? How could we make that better?
Take a video.
Take a video, because if I look at the video, I can see exactly when it's in front of the owl, and I can see the timestamp, and I can see exactly when it's in front of the owl again, and see the timestamp, and then I've taken all the human error out of it, right? That would be an option. What if you don't have video resources? How could you minimize the error? Maybe you can't eliminate it, but how could you minimize it?
You could do.
Bella, go ahead first, and then Bob, let's hear what you're going to say.
I was just gonna say maybe you could do like multiple trials and then try to get an array of times and then maybe take the average or just see what time showed up the most.
Yeah, great. So lots of trials so that you're spreading that error out and you're averaging it out so that you're going to sort of minimize the effect it has. Was that what you're going to say, Bob, or do you have a different idea?
Yes, that's what
Same thing? Okay, great. That's a good strategy. There's at least one more I can think of. Anybody else have another idea?
for more people to.
Have multiple timers. Yeah,
Yeah.
have multiple people time it at the same time and then average their values. I hadn't thought of that one, but that would be good. There's still one more slightly different strategy. So I'll see if I can sort of hint you towards it. So if it's a short amount of time, right? 1, 2, that's like a second or maybe a little more than a second, right? It's a pretty short amount of time. So if I'm off by just a 1/10 on the front end and a 1/10 on the other end, I might be 20% wrong, right? If it's a 1 second and I missed it by 2/10, I'm 20% off, 20% error. But what if I time it for 1, 2 cycles? Now it's about 2 seconds, and maybe I'm still 2/10 off, but now it's only 10% error. What if I go 5 cycles, 10 cycles, 20 cycles, right? The more I do, if I go 1, 2, 3, 4, 5, 6, okay? So now I know the time for 6 cycles, but the error would only be at the beginning and the end. And I've got a longer amount of time, so it's a smaller percentage. And I would just take the total time divided by 6. So I didn't eliminate the error, but I have minimized its impact. Does that make sense? So those are all kinds of strategies you would want to think about. How could you minimize the error? How could you change the procedure or the measuring technique to improve the results? So the big thing about doing these labs, the fun part is doing them, obviously. The important part, though, in terms of being good at FRQs is having these conversations, thinking through how would we measure things? What would we measure? What would our technique look like? How could we improve it? And then in terms of the results, okay, well, let's say you use the mass, like you have the mass hanging down here for the force. Well, you make a table. What is it with 100 grams, 200 grams, 300 grams, 400 grams? You just get a bunch of different mass values, convert them to weight, and then you'd have to decide, does it make more sense to put the weight on the y-axis or on the x-axis? And we're comparing everything to acceleration. And we haven't even talked about how we would do that yet. That's coming later in today's lesson. But we would say, okay, well, I'm going to put the force of weight on one axis and the acceleration on the other. Then I'm going to put the radius on one axis and the acceleration on the other. Then I'm going to put the velocity on one axis and the acceleration on the other, and start analyzing it. Is it linear? Is it not linear? Does it seem to have no relationship? Are the dots just all over the place? And that's actually a possibility. In fact, that's one of the things, if we were doing this in person, it's the one missing piece that the simulation doesn't really do. There is one of those that actually has no bearing. It doesn't make a difference. And so usually it's interesting to watch the students analyzing their data, and they're doing like quadratic and inverse and everything, like nothing works. It just won't come linear. And so finally they start to realize, oh, maybe there's no relationship. And so sometimes when the data doesn't make sense, it's not that you messed up. That's usually the student's first reaction. We messed something up. And actually it might just be there's no actual mathematical relationship between these two things. And so that's the key. Now, we're going to do a simulation that's going to help you kind of figure out what the relationships are. And through our notes today and Friday, you're also going to start to maybe anticipate what those relationships are. But that would be the process we would go through if we were doing this lab in person in a normal scenario. All right. And if you really want to do the lab yourself, easy to make, easy to collect your own, well, maybe not easy to collect your own data. You kind of need a partner. But maybe you can get a brother or sister or a parent to help you if you really want to do that and try it yourself. It's not a hard one to do. All right. But the simulation also does a nice job of helping you figure those things out. Now, the next one we're going to look at is, have you heard the saying, when pigs fly? Like someone will say, hey, when are you going to do that? Oh, when pigs fly. Basically, never, right? I'm not going to do that. Well, we actually are going to make a pig fly today. So hopefully once it zeroes in on me back here in the back part of the room, the camera will find me. And I have a little toy pig hanging from the roof here. It's just a string. There's a hook that's up in this part of the roof. So I've got it on the hook inside the ceiling there. And the string is just hanging it down. So it's just, I can create a little pendulum here or whatever. But this is a battery operated pig with wings. And the wings flap. All right, so now we're actually going to make this pig fly, and this pig's really talented at flying in circles. I've been training him for years, and he's really getting good at it. All right, so we're going to watch this pig fly. So as he kind of settles into his motion, you can see that there's a pretty good steady circle, right? He's kind of gone into a nice steady circular path. And if we think about all the forces that are being exerted on this pig, the pig has weight, right? So there's a weight force pulling it down. The wings are providing some sort of lift force because it's not falling down. And the tension of the string is providing some support so it's not falling down, right? All right, so let's give the pig a rest here. He's getting tired, I can tell. So the goal of this one, and I've actually seen an FRQ like this. They didn't have a flying pig, they had a flying cow, but it was the same scenario. All right. And basically the goal was find the tension in the string. So right now, if it's not flying, what's the tension in the string equal to?
The weight.
The weight. Yeah, because it's not rising or falling, it's just hanging. So the weight would be the tension in the string. What if it was hanging at an angle somehow? That would be odd, but would the tension in the string be the weight anymore if it's at an angle? What would the weight be the same as? Yeah, this is an angled force. What do we do with angled forces? Break them into X and Y components. So the Y component would be the weight. The X component is what we're going to call the centripetal force. It's what we're going to be learning on Friday. We'll sort of tease it today. Okay, we'll dig into it more on Friday. There's a center seeking or circular force pulling it back to the middle, which we call centripetal force. And that would be the X force, the X component. And that's what keeps it going in a circle. And so if you could figure out what that circular force is, the X component, so you would know the X component of the force, you know the weight is the Y component. You got two sides of the triangle. How do you find the hypotenuse? Pythagorean theorem. So it's not a super difficult problem, but it's often one that they'll have something like that on an FRQ where you have to think through, oh, it's an angled force, break it into components like we've done before. So that's when pigs fly. All right. The next one that I want to do, last one, this is the hardest one to catch on video. So let me unpin this one. And I'm going to pin this one. So I got to start sharing the video here. All right. And you guys will probably, even those of you that are here, you'll probably want to stand up so you can see this too. So we got to do this one on the ground because the tables aren't big enough. All right, so, and you can do this one at home too. If you have a pool noodle, or if you have a hula hoop and a tennis ball or a baseball or a golf ball, you can do this demonstration and you can witness it. So if I roll this ball over to Hannah or Sophia, go ahead. If I roll it or she rolls it, it just goes in a straight line, right? It doesn't curve. So to make something curve and travel in a circular path, we need a force. And so if you can kind of see the ball rolling in the video, it's a little bit hard, but you see kind of the tip of it rolling along that ball or that hoop. The hoop is providing a force pushing the ball to the center so it doesn't go straight. I push it straight, but the hoop pushes it to the middle so it keeps going in a circle. Now, when I push it and then take away that force, it goes in a straight line. See if I can get it to go right towards the camera. Close. Grab that for me. We'll try one more time. So as soon as the force is taken away, it travels straight. It doesn't curve. Now there's going to be some slope to the floor and some roughness to the carpet. But the point of this one is that you need a force to make something go in a circle. You don't need a force to make it keep going straight. And so when we take away the force making it go in a circle, when it leaves, it goes straight. All right. So if you want to witness this yourself, you can make your own contraption with a hula hoop or a pool noodle, and pretty easy to demonstrate as well. All right, so hopefully you can see those things well enough. And that is our sequence of demos for the day. Any questions about any of the demonstrations? All right, let me shut this video down here so I don't get you seasick. All right, so now that we've talked about a lab, talked about some demos, let's go ahead and switch gears and take some notes here. Because Unit 7 is, see if I can get this, there we go. Because Unit 7 is often one that students find challenging, I have put a ton of videos on to Access for you in Unit 7, and Unit 7 is where we're at right now. These are just a handful. These are some of the videos that I think are entertaining and educational. But I put that on there mainly to remind you they are actual links, so I could show them to you. We don't have time, but those videos might help you understand some of the concepts we're going to be learning. And today we're going to focus in on the kinematics of uniform circular motion, right? The kinematics of uniform circular motion. Now we've studied kinematics and we learned kinematic equations. What are the things we measured or calculated in those kinematic equations?
Velocity.
Velocity, good.
Displacement.
Displacement,
Acceleration.
acceleration. One more.
Time.
Time. We're going to measure those same things with uniform circular motion. But you've already kind of clued into some differences. So earlier, I think it was Sophia said, we could measure the circumference from, or determine the circumference from the radius and count the time. And so she was already recognizing we can't measure the speed the same way as we were doing, or the velocity the same way, because it's not going straight from point A to point B, it's going in a circle. So we have to think about it a little bit differently. But it's still going to be a velocity or a speed. We're still going to use that. Time is just the same, like time's a scalar, so that's easy. Displacement though, will displacement be the same? I see Greer shaking no. Why is it, how's it going to be different, Greer?
It's gonna be just like you go from the beginning and then it goes in a circle, but I don't really know.
Okay. So what Greer just said, starting at a point, going back around in a circle, what's actually the displacement if we use the same description we've used before?
0.
0. That's not going to help, right? So any other ideas? What could we use instead?
Distance. Or yeah, distance.
We could, okay, how many times does it go around? And so what are we going to relate that to? We've already kind of said it. Like if it goes around twice, we would take 2 times what?
The circumference.
Circumference. So our displacements are all going to be based on the circumference. Did it go 1 loop, 2 loops, 1.5 loops? It's all going to be based on the circumference now. So a slight twist to that, but we still have to do it, right? We're still going to use displacement. And then the acceleration, this is where it's going to get a little trickier. So I'll hold off on that. All right. Not necessarily trickier, but more different, maybe not as easy to anticipate. All right. So in previous chapters, we've considered topics at rest and topics moving in a straight line. Now we're going to be looking at things that go in a circular path, like a merry-go-round, like a Ferris wheel. Just kind of an intro statement. Can I get someone on the Zoom to read this slide for us?
Sure. One of the main differences between linear and circular motion is that circular motion repeats. So instead of measuring the total time it takes for an object to get from point A to point B, we can measure the time it takes to go around a circle once.
All right, thanks, Nico. And that kind of relates back to what Greer was saying. It's going to go not point A to point B. It's going to start in a spot and end up back in the same spot because it's going in a circular path. So we don't really want to measure even time the same way exactly. It's still just time, still a scalar, but it'll make more sense to measure the amount of time to make a revolution as opposed to from point A to point B. So again, slight twist in our mentality of how we approach it. Not complicated, not hard to do, just a slight shift in our thinking. Side comment, I know a lot of you guys are taking down some notes. If you lose connection, your Zoom cuts out, your internet cuts out, these notes are also on Axis, so you can look at them later if you miss something or if your video cuts out or whatever. It's there. And as you know, we're videotaping this too, so the video will be up later too. All right. Now, we've called this UCM, is the acronym for Uniform Circular Motion. Could I get one of you here in the room to read this one for us?
Uniform circular motion, motion in a circle of constant radius at constant speed. Instantaneous velocity is always tangent to the circle.
I'm just going to give you a few seconds to be quiet so you can write some of this down. There's a couple key things there. So we call this uniform circular motion, and the uniform part of that title is referring to the fact that while we're analyzing it, we need to keep the radius constant. So if we were doing an experiment, we might do one trial with a radius of 20 centimeters and one with a radius of 40. But for each trial, we would need to keep it consistent. We also need to keep it at a constant speed. So again, if we were doing an experiment, we could change the speed from trial to trial, but to analyze it, it needs to be at a given constant speed for all the math to work out. And then the last little bit there, the instantaneous velocity is always tangent to the circle. And they're showing it here with our green arrows. Remember, a tangent is a line that touches the circle at exactly one spot and one spot only. All right, let's move on. Can I get someone in the Zoom to read this one for us?
I can read it.
Thank you, Bella.
The direction of velocity is always changing, but the distance from the center of the circle remains the same, constant radius, and so does the time it takes to travel completely around the circle.
All right, so here's my question to you. Based on uniform circular motion, constant speed, constant velocity, or sorry, constant speed, constant radius, is an object moving at uniform circular motion or in uniform circular motion, is it accelerating?
Well, constant velocity, no.
I'm seeing some yeses and nos. I'm seeing some heads shaking and hearing both. So if we go back one slide, just real quick, there's a very intentional word choice here. Constant radius, okay, and then the intentional word choice, constant speed. Any idea why we would say speed, not velocity?
Oh, because velocity is with displacement.
Close.
Change of.
Well, that's true, but there's a, what were you saying, Bob?
It's going to change of directions. It's a vector, so it will change the direction.
Yeah, so if you couldn't hear Bob, he's kind of sitting further back. Velocity is a vector, so it has to be, direction has to be considered, and it could be changing direction. And in fact, as Bella just read, it's always changing direction. So we said it's constant radius and constant speed, very intentional to use the word speed because speed's not a vector, it's what?
Scalar.
Scalar. So direction doesn't matter. So the speed that it's moving in terms of circumference based on time is constant, but its velocity is always changing as a vector because its direction is always changing. Every instant, the ball is now traveling at a different tangent line, right? Its tangent line of direction is constantly changing. So does an object in uniform circular motion accelerate? Always. If it's in uniform circular motion, it has to have an acceleration all the time. All right, so here is what we call that acceleration. The acceleration is called centripetal. So I mentioned that word when we were talking about the flying pig. Some books use the word radial instead, but most call it centripetal acceleration. And we're going to prove later why, but centripetal acceleration always points to the center of the circle. And with the stopper on a string circling over my head, that kind of makes sense. What's the force in that scenario of the stopper swinging? What's the force that keeps the stopper going in a circle? Why doesn't the stopper go straight? What's the force that makes the stopper go in a circle?
The weight of the math little, I don't know what to call it.
So if we have a metal thing hanging, it's the weight that's hanging. What does that weight create? What kind of force is it generating in the system? Because the stopper is not touching the weight. Tension, yeah. So it's the tension in the string that keeps the stopper going in a circle. And it's the weight hanging at the other end or your finger pulling on the other end that creates the tension, right? But it's the tension in the string that makes the stopper go in a circle. And so if you think about the tension in the string goes from the stopper to the center of the circle at all times, right? No matter where the stopper is, the string goes from the stopper to the center, from the stopper to the center. And that's the force. Well, what's true about the net force and the direction of the acceleration? Always the same. The net force direction and the acceleration direction are always the same. So if the string is pulling it from the stopper to the center with a tension force, the acceleration has to be from the stopper to the center. All right, the next few slides I'm going to go through fairly quickly, and it's a combination of pre-calc, trig, and geometry. And it's because not all of you have had all of that math yet. I'm going to go through it relatively quickly. It's not something you would be tested over. It's just something that if you have the math background, and I'll try to explain the math as we go as much as I can, but I don't want to spend too much time. But if you have the math background, then it may help you understand some other reasons why the acceleration points to the middle and actually how we can actually calculate the value. Because there is a specific equation for it that is not like the other kinematics equations we've had before. And that's what you're going to learn is in this uniform circular motion and then in rotation after ski week, the equations are different. We're going to have a whole bunch of new equations. All right, so let's go through the math and see if this makes sense to you. Like I said, not something to be tested over, but maybe help you understand where the equations come from. So if we look at the change in velocity in the limit that the time interval becomes infinitesimally small, we see that we get two similar triangles. So that sentence explains what we're going to be trying to do on the next few slides. And I think it's probably a pre-calc topic to understand limits. So if you haven't learned that yet, it's not a big deal. I'll try to explain it fairly simply. And the way you may hear it worded is instead of saying becomes infinitesimally small, sometimes you'll hear it phrased as it approaches zero. That's another way you might hear that phrase. So what we're saying is right now we've got V1 and V2, and they're not the same velocity because the ball's at a different position. So they might be going at the same speed, but the direction's changed. And since the direction's changed, they're two different velocities. Now, what's the dashed line on that triangle on the left represent?
The displacement.
Yeah, it's straight from A to B. That's the actual displacement of the object. Let's just say the stopper. We'll just keep with that scenario. So the stopper is going straight from A to B in terms of displacement. But did it actually travel that line? It traveled the arc, right? What's longer, the arc length or the secant that connects the 2 points?
Arc length.
The arc length is longer, right? That makes sense? Now, if I make the time between those shrink, then the displacement is shorter and the arc length is shorter. If I make it even less time, they get closer and closer and closer. And that's what they're trying to show you here is if we keep getting closer and closer and closer to the point where time is approaching zero, it's the difference between them is very, very tiny. What's going to be true about that displacement dashed line and the arc? Are they going to become more similar or less similar as they get shorter?
Yeah.
They're going to be more similar, right? The longer the secant and the longer the arc, that arc's got a big curve to it. The secant cuts the corner basically. That's a big difference. But if you make it smaller and smaller and smaller and smaller, they become more and more and more alike. That's how we're going to convert this into triangles by basically taking our triangle and converting that down to where there's basically no difference between the straight line and the curved arc length. So that's one of the principles we have to understand. All right, the next principle is if we think there's two circles here, so the left, if displacement is equal to velocity multiplied by time, we learned that last semester, then V times T is the displacement covered in the time. So now we're not showing it infinitesimally small, we're showing it big enough to see here just for visualization. But now it's not a dashed line anymore, now it's just that straight line. If the time were infinitesimally small, it would basically be the same as the arc length, or very, very close. Now, we said uniform circular motion means constant radius. So the radius at velocity 1 and the radius at velocity 2 would have to be the same. So what kind of triangle is that?
Isosceles.
An isosceles triangle. We've got two legs that are identical and then a base. Now, if we look at that a little bit different, that's one way to think about it. We've got radius, radius, and the displacement. We could also think about it as I've got velocity 1 and velocity 2. And if I create the third resultant of that triangle, That's the change in those two velocities in terms of direction. Because this point, this point, this point, this point, because the starting points are the same, the theta, the angle, has to be the same. So this angle in the second triangle over here to the right, and this angle in the initial triangle on the left have to be the same angle. Now the delta V doesn't equal VT, and the radius isn't the same as the velocity, but the angle has to be the same. And because the speed is also not changing, the speed is constant, the magnitude of V1 and the magnitude of V2 also have to be the same. So that's also an isosceles triangle. So we have two isosceles triangles with the same angle. That means they are similar triangles. So now we're going to some trig and geometry connections here. So now let's look at those two similar triangles. If they're similar triangles, we can set up a proportion. So we've got the blue proportion, where we're going to take the base, delta V, over the velocity, which is one of those two isosceles legs, right? We're just finding the proportion for the blue triangle of base to side. And then for the red triangle, we're going to find the same relationship, base to side. But in this one, it's displacement VT over R. Now, R doesn't equal V1 or V2 necessarily, but proportionally, the base to the side has to have the same proportion because they are similar triangles, both isosceles with the same angle. So proportionally, they should be equal. Now, if we just do a little algebra and multiply both sides by t and divide both sides, if we multiply both sides by v and divide both sides by t, we end up getting delta v over t equals v squared over r. What is delta v over t? What is the change in velocity over time?
Oh, the acceleration.
Acceleration. So we have using pre-calc to be able to think about it as triangles and geometry and trig to recognize they're similar triangles and set up a proportion. We have shown how we can find the acceleration for something moving in a circle. It would be the velocity squared over the radius of the circle. And so we're going to come back to that equation. That equation actually is one that College Board gives you. It's on this one right underneath the friction equation. So it is there. And they actually put a nice little subscript C for circle or centripetal. So it's there for you, v squared over r. Now again, you're never going to need to prove this mathematically. You're not going to have to show the pre-calc and the geometry, but if that helps you understand that this equation isn't someone's, epiphany, it's just math, then that may be beneficial for you. The last thing I want to show you with this math connection, then we're going to start picking up the pace a bit. If we think about that second scenario where we've got the two velocities and we actually connect them as a triangle on the circle, you can see that the delta V points to the center. So that is more mathematical proof that the change in velocity, which is the acceleration, points to the center of the circle. So just another way to sort of visualize the things we've already defined and stated are true. We're trying to prove them mathematically so that you don't think it's wizardry. It's not sorcery, it's just math. All right, now let's dig into more of the physics. So here is a nice summary. Can I get someone in the video room to the Zoom room to read this slide for us? Nice summary here.
I'll do it.
Thanks for saying.
This acceleration is called the centripetal acceleration. Its direction is towards the center of the circle. Its magnitude is given by a equals v squared over r.
So you'll want to make sure you get that into your notes. Like I said, it is provided by the AP College Board list, but good to have in your notes. You're going to need that as a quick reference point for these next two practice questions. So for question 17 here, or question number 1, sorry, slide 17. If you will read, I'll read the question and then you put your answer in the chat. Is it possible for an object moving with a constant speed to accelerate? That's question part 1. Part 2, explain. So that means every answer has 2 parts, yes or no, and then an explanation. Both have to be true. A, no, it's not true. If the speed is constant, then the acceleration is equal to 0. B, no, it's not true. An object can accelerate only if there's a net force acting on it. C, yes, it is true. Although the speed is constant, the direction of the velocity can be changing. And then D, yes, it is true. If an object is moving, it is experiencing acceleration. So go ahead and put in the chat, which of those answers do you think is the correct answer? So how about you guys? What do you think? We have a bunch of C's over here. So we're saying C in the chat. I'm also seeing a bunch of C's coming through, and that is correct. I want to highlight two of the incorrect ones. Is there any part of B that's true?
The explanation.
The explanation is actually true, right? It is true that an object can only accelerate if there's a net force, but the answer isn't no, it should be yes. So you do have to be careful that you don't get tricked by them giving you a partial truth, okay? And then in the last one, it is also partially true. Yes is right. The explanation is the wrong part. An object that's moving doesn't have to be accelerating. An object moving in a circle does, but an object that's just moving could be moving in a straight line at a constant speed and velocity. All right, next question. Same scenario. Put your answer in the chat. Consider a particle moving with constant speed such that its acceleration of constant magnitude is always perpendicular to its velocity. A, it's moving in a straight line. B, it's moving in a circle. C, it's moving in a parabola. D, none of the above is definitely true all of the time. When you think you got it, go ahead and put it in the chat. How about here in the room? What do you guys think? All right, I see a few signals for B. I see a bunch of B's coming through in the Zoom chat, and it is true. If it's moving in a circle, those things have to be true. If it's moving in a straight line, they can't be true. If it's moving in a parabolic path, it is sometimes true. But for a circle, it's always true. And so that is the correct answer. All right, next question. An object moves in a circular path at constant speed. Compare the direction of the object's velocity and acceleration vectors. A, they're moving in the same direction. B, they're moving in opposite directions. C, they are perpendicular. Or D, this question is meaningless since acceleration is 0. All right, seeing some quick answers in the chat, a bunch of C's. I see a bunch of people signaling C here in the classroom too. They are perpendicular. All right, question 4. Two cars go around the same circular track at the same speed. The first car is closer to the inside of the circle. Which of the following is true about their centripetal acceleration? Both cars have the same centripetal motion since they both have the same speed. Let's just go through them and is that true or false? Give me a thumbs up or a thumbs down on the Zoom. Is A true or false? A bunch of thumbs down. Yeah, if the speed is the same, that just means it's uniform circular motion. It doesn't mean that everything about their motion is the same. Okay, just that it's uniform. All right, part B. The centripetal acceleration of the first car is greater since its radius is smaller. Thumbs up or thumbs down? All right, Nico, you were one of the first thumbs up I saw. Can you tell us what helped you draw that conclusion?
For B, right?
Yeah.
Since it's a tighter circle, the radius is smaller, the acceleration, the centripetal acceleration has to be greater because it's a tighter churn, so it has to like churn more, I guess you could say.
Good, good. So you're thinking about it very conceptually. Looking at the equation, you could even think about it mathematically. The radius is in the denominator. So if you're dividing by a smaller number, you get a larger answer, right? Good. All right. The last part is going to be probably a little bit easier. Most of you have learned about this in Algebra 2 when you studied things like, unless you're just in Algebra 2 now, then you may not have gotten to it yet. But sine waves, cosine waves, or in some other classes, you may have heard these terms before, like period and frequency. And then we're going to connect those two things to rotational velocity, or sometimes it's called angular velocity, or circular velocity, or tangential velocity. It has a lot of synonyms. But period and frequency are the two terms that are new to our class, but probably not new to that many of you. So let's go ahead and cover them. Could I get one of you in the room to read this one for us?
The time it takes for an object to complete one trip around a circular path is called its period. The variable for period is t. Periods are measured in units of time. We use seconds.
All right, good. So a real important fact here is notice that the T is capital. For period, you must use a capital T. For regular time and linear motion, we use small t. For circular motion and period, we use capital T. That's how we can distinguish, is this the time for a revolution, or is this just the time more generally speaking? And in this case, capital T means the time for one revolution. It's specifically referring to the period. And there are multiple equations on this College Board handout that give you period-related equations. And so we need to make sure you keep track of that T being capital. Now, if that definition works for you, maybe you've learned about the concept of period before, pretty easy, great. If not, there is a way you can kind of represent it as sort of an equation. And this is not really a formal equation. This is not on the AP formula list. But if having a mathematical relationship helps you, we can also think about calculating it as taking the time in total divided by however many revolutions it has traveled. And that would give us the period. So back to our stopper lab, like we were saying, one way to minimize the error is to count a bunch of revolutions and then just take the total time divided by how many there were, and that would give you the period. So again, this is not a College Board equation. This is one that might be helpful to you if it helps you sort of think it through mathematically. Remember, I have said a couple times this year, there are sometimes equations that can be helpful that aren't on here, and you may want to add them in a central location in your notes or even on the page, the side of this that's half blank. This is one that if you find it helpful, this could be something you could include there. And in fact, in this unit, these 2 weeks leading up to break, and especially the 2 weeks after, there's a lot of equations that you'll probably want to be adding to this central hub of information for you. All right, the next term is frequency. Could I get someone in the Zoom to read this one for us?
I'll read it. Another useful measurement in circular motion is how often a cycle repeats. For uniform circular motion, the number of revolutions that an object completes in a given amount of time is called the frequency of its motion. The symbol for frequency is a little f, and the units we measure with are hertz per second.
Very good. And Bella, you're the first student that actually emphasized that it's lowercase f, which is good because it's important. Just like the T has to be capital for period, the F has to be lowercase for frequency, so we don't confuse it with force because we use a capital F for force. So we need to use a lowercase f for frequency. And sometimes you'll see it given in per seconds or seconds to the -1 power, which is 1 over seconds. But normally you see it given in hertz. And hertz is a weird word, but it's just named after a scientist to honor that scientist. And we abbreviate it with a capital HZ because it is his name, his last name. And if you recognize this definition, it is the number of revolutions per time. So how does that compare to period?
Period is one time.
Say that again.
Period is one time, one trip around in the circle.
Yeah, the period is the time for one trip. So it's time per revolution. This one is revolution per time. So how do they compare?
Inverse.
Yeah, they're inversely related to their reciprocals. All right, so let's keep moving. If you would like to have a mathematical formula to help you, you could say this would be N over T, revolutions over time. And if you've driven, did any of you three drive yet? Sophia, okay. How about in the Zoom? Did any of you guys drive yet? Few people nodding, okay. So you probably, whether you've driven or not, you may have seen in the car the RPM gauge that shows the revolutions per minute the crankshaft is spinning. So that is a type of frequency. It's not measured in hertz, it's measured in RPMs, but it's still a frequency. How many times is it revolving per unit time? All right. So as we said, based on their definitions and also based on these simple little relationships mathematically, we can see that they are truly inverse of each other, or we could call them reciprocals. And recognizing that they're reciprocals makes it nice and handy in solving certain problems, because if we know the reciprocal and you need to use the period in the equation you want to use, but they gave you the frequency, we'll just take 1 divided by the frequency, and that is the period. So knowing that they're reciprocal is important. Another way to imagine that mathematically, or envision that mathematically, is to just say the period t is 1 over f, and the frequency f is 1 over t. Right? They're just reciprocal of each other. And using that inverse relationship can help you solve problems when they give you the one that's not as helpful. Like they give you period and you want frequency, or they give you frequency and you want period. Knowing they're reciprocal is beneficial. All right, now the last topic of the day. What about velocity? Whoops, the wrong thing here. Trying to slide this down. There we go. So velocity, what we call tangential velocity, is the velocity that if the string on the stopper broke, it would go at a straight line, like the tennis ball. When I lifted the hoop, the tennis ball went straight. If the string broke, the stopper would go straight. I mean, it would fall to the earth, but in terms of its path, it would be in a straight line. Well, we learned back in first semester, and we've been using it all year. Speed is just distance over time. And if we're going to think about something moving in a circle, and this is actually the slide that basically Sophia quoted for us at the beginning of the class. For an object moving in a circle, we really want to know how much time does it take to make one revolution, which we now know we're going to call period and use capital T to represent it. And we know the distance around the circle is the circumference. We've also talked about that today. So hopefully you're getting, whoops. See if I can, I'm not sure where this extra space came in. There you go. Hopefully that didn't mess you guys up too much visually. But we know that the period is the time it takes to go in a revolution, and we know the circumference is the distance it travels in that revolution. So you're probably starting to piece together how we're going to substitute those things in. And this is what the next slide shows us. If we know circumference can be calculated as pi times diameter, or 2 pi r, pi times double the radius, and we know the time it takes to go around is period, or capital T, we just substitute circumference 2 pi r in for d, and we substitute capital T period in for t. And our tangential speed, or the velocity that this object has tangent to the circle, would be 2 pi r over capital T, 2 pi r circumference over the period. This equation is also not given by College Board. Okay, so this is one that is very helpful, and you could think it through based on what we've learned today. You think, well, it's just circumference divided by period. You could process that mentally, but sometimes in the heat of a test, the adrenaline and the stress, having that equation committed to memory could be helpful. So that one is one they do not give you. All right, so let's go to the last section on this part, a nice little summary. Can I get someone in the room to read this one for us?
Velocity is a vector, so it must have a magnitude and a direction. The magnitude of an object's instantaneous velocity is its speed. V equals 2 pi r over period. If an object is in uniform circular motion, the direction of its velocity is always changing. The velocity is tangent to its circular motion.
All right, so hopefully everything on this slide you already have in your notes. The velocity is tangent to the circle. It's uniform, therefore the speed is the same, but the direction is constantly changing. And so it does have a tangential speed, which we can calculate with this formula. Now, again, sometimes you may want to use frequency though. So what does T equal in terms of frequency?
1/over frequency.
Yeah. So frequency is 1/T and T is 1/frequency. So if we use a substitution, we could also write that the velocity tangent to the circle would be 2 pi r times the frequency. So you had another form of this relationship. Again, that one is not on the formula list. So if you find it helpful, maybe one you want to jot down in your growing collection of equations that can be helpful but aren't provided by College Board. All right, we just have 2 questions to practice and we're done. Give a few more seconds to see a few people still writing, it looks like. All right. Back to the stopper. We started here, we're going to end here. A girl whirls a toy at the end of the string around her head. The string makes 1 complete revolution every second. So I'm going to pause there. What's the period? 1 second. Good. She keeps the radius constant, but increases the speed so that the string makes 2 complete revolutions per second. What happens to the centripetal acceleration? Does it stay the same? Does it double? Does it quadruple? Does it get cut in half? So think about it. Put your answer in the chat. See what's coming up on the chat down here. Got several votes for C, it looks like. What do you guys think here in the room? Do you agree with C?
Mhm.
Yeah, so the velocity says they're increasing the speed and they're making, instead of it going 1 revolution, it's going 2 revolutions. That means the speed is now twice, right? They double the speed, and in the equation for acceleration, it's squared. That means the acceleration will be quadrupled. All right, last question. A ball is swung in a circle. The frequency of the ball is doubled. By what factor does the period change? Put it in the chat when you've got an answer. Seeing quite a few votes for B. Do you guys agree with B?
Mhm.
Yeah, if we double the frequency, we're cutting the period in half. All right, good. So the assignment is an intro worksheet to let you practice with all these different equations we've been learning today. So let me go ahead and stop sharing this and show you where to find that in case you're having difficulty. Probably you wouldn't be. You guys are pros at this by now. But on the Access page, you're going to want to go to Topics. We are now on Unit 7, Uniform Circular Motion and Rotational Motion. And over here on the right, underneath the picture of the merry-go-round, you can see Uniform Circular Motion notes. Now, those are from last year, so some of the slides might be slightly edited or moved around in position, but basically it's what we covered today and a bunch more stuff we'll be covering in future days. Right underneath the notes is the motion intro worksheet. That is what the assignment is. And then right underneath that is worksheet 1. So I want you to come to class Friday with that intro worksheet complete. And then on Friday, we will do the worksheet 1 together in class, right? If just to make sure you're looking at the right worksheet, this is what the intro worksheet looks like. Make sure you print the right thing. It has basically all the equations we learned in today's lesson at the top. Slow to open here. There we go. All the equations across the top, and then 4 questions with 3 parts each, making sure you know how to apply those equations. All right, so I'm not going to have you turn this in on Axis. I'm just going to have you come to class with it and have different students explain different answers. So just come with that completed on Friday. And for today, we are done for the day with not too much time to spare, actually. If you're in the Zoom and you have some questions for me, feel free to stick around and ask them. But if you don't have any questions for me, you can be dismissed at this time, and I'll see you tomorrow for our AP exam review time.
Thank you.
Yeah.
Yeah.
You're welcome,
Thank you, Mr. Whip.
Nico. And then for you guys that are here, you're welcome to work on the worksheet. If you want to play with, try out the pig, if you want to experiment with any of the force things we got set up, if you want to do any of the, this is like a chance for you to also do some hands-on little experimentation just for fun. You're welcome to do that as well.
So the frequency is 1 over the period, right? So for the first question, the frequency is 1 over 4 hertz.
Let's see, yes, so 0.25 hertz or 1/4 hertz. Usually we want to use decimals so that we can show sig figs.
Yes.
What should our units be for velocity?